bij deze sessie DC-systemen in de praktijk. Ik wil graag mijn internationale collega Pavel Purkat aan jullie voorstellen. Hij is application specialist en hij zal nu het woord gaan voeren in het Engels.
Yeah, thank you very much for the introduction. And thank you also for the invitation. It's always special for me to be in the Netherlands. A little background before I start talking about the topic. I come not from the Netherlands, but I did study here. So I studied in Delft University. I did my master's and then stayed for research. I was a PhD researcher and finished my PhD there on the topic of DC microgrids and solid-state circuit breakers. And it was really a nice period of my life. Now for the last 5 years, I've been living in Austria. Now, I split the presentation into 5 big parts. First part is really why we talk about DC so much lately. So this covers some megatrends that I think are important to understand, why it's such an opportunity. Second part is where do we stand today? There I try to give you an overview of the existing associations, which you might know some of, and also the materials or tools that you can find useful. And then third and fourth section are a little bit maybe more theoretic in the way it collects experiences and knowledge from our previous projects in DC and covers the fundamentals, what we need to cover when we are designing a DC grid. And the last part is a design scenario of a microgrid that we are developing in one of our locations in ABB. So the first thing that the megatrends, as I mentioned, probably you are quite knowledgeable about those already, but why they matter for DC in particular. The growth of electrification. What you see, I think, and why I would like to mention this is we had traditionally the industry and buildings. These were the 2 big sectors, and we didn't almost talk about anything else. But with the electrification of transportation and data centers, suddenly we have 2 big new parts that are completely new sectors, and they are growing with very fast rate. Moreover, think about it this way. It's an infrastructure when you are building a data center, right? The data center has a lifetime of 15, 20 years. But the servers inside are updated every 5 years. The power level of that server doubled last 10 years every 5 years, right? So you need to also project your infrastructure needs for that need in the future. And this poses a challenge. And another big chunk that is very small today, but will be very big, is the hydrogen. And very often so far forgotten. Similar story. For sources, there is a revolution, quite silent going, but in the last 20 years, we already went to more than 50% of non-fossil fuels in Europe. This is a big jump, and you can see that with solar and wind, there is an inception, right? We passed the knee, and now the energies are growing quite fast. The cumulative growth is very fast, while the coal and probably also gas will go down. The only question mark is the nuclear energy with the small modular reactors. Maybe there will be again uptake in this source of energy as well. And third is the energy storage. The energy storage, when I started studying engineering in 2011, or let's say masters in 2014, we almost never spoke about that. I think today the master students or bachelor students or whoever doesn't talk about anything else, because it's such an important topic and it's a huge opportunity for us, because the battery energy storage inside is DC, right? And all of these changes had a profound effect on how the power distribution system looked like. 30 years ago, maybe 40 years ago, the energy was supplied by large rotating machines connected to transformers, and then either distributed to the distribution. We had step-down transformers, our houses where we had mostly lighting, maybe some sockets, no big loads. And in the industry, big rotating machines, again connected through transformers. What changed is all the red parts. In generation, we have a lot of wind, or much more, solar, hydrogen coming in. We are connecting generation storage together with the solar plants to fight the intermittency. We use storage in utility to provide frequency support. And I mentioned data centers, variable frequency drives, and distributed energy storage and generation in the sites. All of that is based on power electronics. Colleagues from Aalborg University few years ago estimated that approximately 70% of today's electricity is processed by power electronic devices. Converters inside almost always use DC. So the reason why we talk about DC so much is not necessarily because congestie is such a popular Dutch word nowadays, but it's because we have so many converters that suddenly it starts to make sense. Because if we build a system in AC that is mostly composed of converter-based sources and loads, we get this. We get a lot of power conversion steps, we get a lot of filtering, and these systems, they can still be great, and it still makes sense to use them. However, in some cases, especially when we have a lot of storage present, it starts to make sense to think differently. Because each time I interface storage through another conversion step, I lose on efficiency and then reduce my effective storage that I can use. And this is why DC makes sense in some particular places. It tends to be more efficient, it is simpler, at least on a paper, and it is resource effective. We don't have the high voltage peak, we can utilize the full voltage, you can usually increase the, the copper usage quite nicely. So, plus, you don't have as many big transformers. You don't need so much copper, so much steel. So, where are we today with the DC systems? To answer that question, I would start 10 years ago. In 2013, ABB released the first DC ship. It was called Dynastar. And one of the big reasons why it was interesting to go to DC were the big transformers. They wanted to get rid of them, obviously, to reduce space, claim of the electrical installation on ship. And the project, on the left we see the DC ship, was quite successful. After 10 years, there are several hundreds of DC vessels in operation. It's pretty much in the industry recognized that for smaller offshore vessels, the systems tend to be a little bit cheaper to buy, for sure to operate, and they also tend to be a little bit more reliable because you don't have as many components. So where are we with the other applications? In around 2020, there started to be research projects together with the industry in Germany, DC Industry 1 and DC Industry 2, that over the years, with the pilot installation, proved that installing with DC reduces peak power, which is quite handy, especially when you have a congestion problem. When instead of 300 kilowatts for the installation, I need 100, that brings quite significant saving, especially in Europe. It enables recuperation. When we have variable speed drives, when we have the robots, they break a lot. When we use DC, it's very easy to reuse that kind of energy. And the same as in ships, we utilize materials more efficiently. In the meantime, there were several installations, not as pilots, announced by companies in Germany that are building DC infrastructure in their factories. This is a map of the known projects that was mapped by DCID, which is a company I will talk later about. And you see there is, I think, a little more than 50 projects mapped by them from different sectors. Now, in this map, there is one big blank place, and that's China. I don't know how many projects there are, but from what we keep hearing, it's probably more than 100. And for sure, that's the place where a lot of DC technologies are being developed. So where are we, let's say, here in Europe today? We do face some obstacles when it comes to developing DC systems. One of them is products. We don't have that many off-the-shelf products that we can realize more complex DC systems. This is partly caused by the fact that there are not that many standards by which we can produce these products. And last but not least, for example, here in the Netherlands at Delft University, the first DC microgrid course was started in 2016. So we don't also have that many people that have at least theoretical knowledge about the systems, and plus there is a very reasonable fear of going to DC without having enough pilots. And this all makes sense. So we are in a hardware evolution or revolution, and this takes time. It is not like developing software that you can test very easily. We will need more time to develop, but you can see the uptake in the installations already. Also, what suggests the growth of the DC importance are the alliances promoting DC, but also developing the standards. One of them, probably known to most of you, is Current OS. It was started here in the Netherlands a few years ago. By today, it's more than 70 partners. I think it's roughly 100. And it's led by all the big companies that are in the board. Today, also, Mersen is entering the board. I just didn't have time to update the slide. Similar organization, ODCA. This one used to be a little smaller because it was very focused on the German or DACH market and very much focused on the industrial installations. Again, many big players from the automotive industry are leading the charge here. What is interesting, and I do recommend as a free time reading, is to download the DC industry system concept. I will touch on some topics from that, but in less detail than the document itself. And it explains how the DC systems can be designed. What do these these alliances have in common is, first of all, the networks are voltage controlled. I will explain that in a bit more detail later. They do use distributed grid management, so there is usually no central controller. And lastly, for protection, we talk about sectors or zones, so we split the grid in some way to make the protection challenge a little bit more manageable. When it comes to tools that are today available for designing DC microgrid, it would be probably beneficial to check out the webpage of DC IDE or DC Partners. They have developed a web tool which gives you a drop and place design that allows you to calculate power flows, the thickness of the cables. There are some things still not implemented, but they are working on them. But very importantly, there is a very rich library of various converters, switches, disconnectors, contactors, and so on that you can use for your designs. And also us, in ABB, or let's say in Smart Power, we are trying to disseminate knowledge in various application nodes. For example, an application node that will be announced soon, within, I think, next 2 or 3 months, is a protection devices for direct current applications, an overview of all the protection devices needed. We already have released the faults in low voltage DC microgrids that gives an analysis of various fault locations, and 2 new application nodes for protection of 1500 volt systems. So not necessarily only DC microgrid as such, but really practical DC systems, for example, when you have a multi-megawatt converter or a large battery rack using higher voltage, how we can protect that, how we can do that in a safe manner. Okay, I call this part fundamentals because it goes into, well, a little bit of basics. This is one of the first slides that Professor Kruger at the university started his lectures at HVDC. He wouldn't explain it too much at the beginning of the lecture, but he would just say, by the end of this course, you should know that there is no such thing as DC. But to a little bit get into what DC systems I will talk today, let's have a look at the schematic of a system that is proposed by ODCA, but a very similar system proposal comes also from the Current OS Foundation. Normally, of course, we connect to the AC system because we have that already available. We can have isolated or non-isolated connection. It depends on the system itself. In this case, this connection should be isolated because of the type of the smart breaker, as it's called in the description used. We always have a solid-state-based circuit breaker protecting the in-feed, but also the DC sectors. The grid is split into hierarchies. This helps us to design the circuit breakers and the needed connections between them. And very importantly, the loads are not always protected individually, each by a solid-state circuit breaker, because that could be somewhat expensive, as you can imagine. Very often, the sector is protected by a solid-state circuit breaker, And inside the sector, we use more traditional devices like fused switch disconnectors and so on. With this, we can achieve selectivity, and we then decide where do we achieve selectivity. Do we achieve it inside of a sector? Probably not possible. Between the sectors, for sure. Between hierarchies as well. And this is the base where the ODCAs starts from. Now, the asked question, how do we connect to AC system, and what implication does that have for the grounding? Because that's the main thing. If I have both AC and DC, how do I deal with the grounding topic? In principle, grounding of a DC system is not really different than grounding an AC system. We can think of probably the same 4 options, so the protective earth with the neutral combined or divided, grounding on the AC part, or leaving the DC system ungrounded. Spoiler alert, the last option is the most popular. One option is combining AC and DC system together in one installation with common grounding as shown here. So this system is grounded on the AC part. And then we have DC. In principle, here you can have a continuation of the AC, right? So here you can have a connection and in a house, for example. This would be something also from the connection. You can imagine it's a PV inverter used in a house. They are very often grounded. This can work quite well in small installations. One of the disadvantages, you need short circuit current interruption in both plus and minus pole. Because you can have a fault to the ground on the AC side, and you need to be able to operate or to stop the short circuit current in both phases. The other option is to leave the DC system ungrounded. And this is what is being used more or less as a standard in industrial applications with more power, but also in marine applications. In that case, you only need to have short circuit protection in one of the phases, not in both. And you always need here the galvanic isolation, just for the maintenance purposes. But you always need that. And same applies to the loads. Also, in this system, the connection of battery storage or other storage becomes a little bit easier, because in the previous system, we always have, especially with batteries, capacitance to the ground. This capacitance is great at conducting various currents that are coming from your converters, and this is something that should be checked. And the last system that's very interesting, and there are 2 variants of this, is using a midpoint. Now, using a midpoint gives you a big advantage, because instead, for example, of 800 volts, you can split it to plus 400 and minus 400. But there are, again, 2 ways you can do that. You either say, OK, I have plus and minus, but the midpoint is not used as loadable. And this is nice, because you don't have to think about balancing. If you load the midpoint, you will have equalizing currents flowing in your midpoint, and you need to somehow balance it. So you need one more device. But this is a little bit connected to the voltage levels that are available. For example, in industry applications, they do use these systems, especially in Germany, but with the midpoint ungrounded. When we discuss some other applications that use very specific power supplies that were designed for 400 volt DC, now I'm thinking maybe about data centers, they will tell you, but we want to have the midpoint loadable, because we want to connect our power supplies plus to neutral or minus to neutral. So we can have the 800 volt system, but still use the existing power supplies. And this is something, as a recurring topic in DC installations, what voltage do we choose? And that brings me to the next part, which is control. I said that typically the DC networks are voltage controlled, right? So how do we control this voltage, and what controls we need? Depending on the size of the system, the control can get quite advanced and, let's say, a little bit involved. When we have a really, really small system, think of point-to-point connection, we need only this. So I essentially have the loops inside of the converter, nothing else. Now, when I have multiple sources, and think about an installation that, for example, has redundancy in the connection to AC side, has battery energy storage and PV, I somehow need to decide who is supplying power when. right? And this is when I need the power flow management. On top of that, I might have some economic reasons how and when I use my battery, when I don't. When I use PV, probably always when there is, but then it comes the energy management, and this is the highest level of control. About the energy management, I will not talk today, but I will touch a little bit on the power flow management, because the power flow management is tightly connected to the voltages that we need. And now, you will probably see where I was coming from with DC doesn't exist, because the converters in, for example, industrial DC grids, on the load side, are asked to operate in 350 volt band. They have to provide full functionality in this high band. Why they chose such a high band? Partly it's because of the power flow control, but partly it's also because of the interoperability between different brands. For the sources and storage devices, this is slightly smaller the band because they need to control the power flow in these bands. But we still have parts where they still are supposed to provide some limited functionality, and this can also involve providing short circuit current at a low voltage. So how do we implement the voltage control? Essentially, the idea comes from AC systems. Unsurprisingly, many ideas here are reused and recycled, just adjusted, and it's the droop. In AC system, we use the droop for frequency control. In DC, we use the droop method for controlling the voltage. Essentially, what it means, we design a curve for each source converter, so each converter that is able to source current in the system, and we link the current and the voltage with the resistance. And this resistance then gives us how much current is our converter supplying at the given voltage. For example, the PV is quite flat. Only when we are reaching the over voltage levels, then we reduce the power, and essentially we have shading of the power supplied. But for the battery energy storage, we support the system as much as we can. But when the system becomes with the voltage too high, we start charging the battery back. With the in-feed, we always use it, and we use it fully, especially, and with the in-feed, we start also charging back to the grid when that's possible. In this way, we can coordinate the sources between each other without having a communication link. And now, this is one of my favorite topics from the time when I was allowed to do research, and that's the stability of DC systems. It seems that what could be so difficult about that, but as it turns out, keeping the DC grid operating without some nasty oscillations is not that easy. Why? Well, it's an RLC network. Any RLC network will oscillate if you design it correctly or wrongly, in case you don't want to see the oscillations. How can we know when there are going to be oscillations? This is an example taken from a very, very simplified vessel design. Essentially, we have on one side, in one sector, we have a supply that is characterized by the current that it's supplying. This could be an uncontrolled rectifier with an impedance, connected with a bus-type breaker. And on the other side, we have some motor, again, characterized as a current load with some impedance. To know when and if it will oscillate, we need to derive the system transfer function like written here. Now, what this transfer function will give us is the resonance point or the anti-resonance point. It can happen that we don't care because every such a network will have resonance and anti-resonance points, right? You can't avoid it. But what I care about is where is the resonance point. For example, if this resonance point is at 300 hertz, and I happen to have an uncontrolled rectifier that creates a ripple of exactly 300 hertz, then guess what? This is going to get amplified. And this is something you need to predict when you are designing the DC system. And provide sufficient damping at these frequencies, because that's the solution. So here we are then entering the realms of small signal stability, where we say, okay, each of these resonances, they appear as a so-called pole in the complex plane. If the pole is on the right side, what is going to happen? It's going to explode. So it always needs to be on the left side, and ideally not too close to the right side. So we say, okay, 12 degrees or 20% of the damping, as a rule of thumb, gives us a stable system. We see it drawn here. The orange line, it does not have enough damping. The blue line, yes, there is some oscillation, but maybe not too much, and this is something I can handle. Adding too much damping is also not something you want, because it becomes less efficient. And here you have then the steps how you do that. First, derive the transfer function. Second, check the resonant frequency, add damping, recalculate, and so on. Well, honestly, this is quite complicated. And this is what my colleague thought. And I was like, okay, is there some other way we can describe a system? And in this paper, he derived a method how to pretty much check the same thing using what he had to use was some advanced math, but what it came down to was a relatively simple rule that is written here. To have asymptotic stability of a DC system, what I need is to check the capacitance that is available at the load side, the maximum time constant of the system, so this is the LR ratio of the system, the maximum power load that I need to transfer to this load, and the minimum voltage. Essentially, what this simple rule tells us is that, first of all, do we have such an equilibrium of the system? Is this system going to reach an equilibrium? Does it exist? And second, because we talk about minimum voltage, it also tells us that this gives us an adequate equilibrium. Why adequate? Because if you just blindly applied the math, your equilibrium could be at 0 volts. The system doesn't oscillate. It's just not very practical. And that's why it's important to also consider the equilibrium at the minimum voltage where the load will not disconnect. Second important aspect, also coming from the Netherlands, Professor Ferreira, he was at Delft and then later at Twente University, is to consider the skin effect and the effect of higher frequencies on the resistance. For the transient stability, it helps us because essentially it damps the higher oscillations. But at the same time, if we have them present all the time, it will overheat the system. And I'm highlighting the names and saying that where they come from, because I think here in the Netherlands you have a great advantage when it comes to DC. There is already a lot of knowledge. You just need to tap into that. And these oscillations, they lead us to the next logical topic, and that's electromagnetic compatibility of the systems. Same as in AC systems, or very similarly, we either have a conductive interference or a radiated interference. We have common mode and differential modes. Now, the problem in DC system, as far as I know, there are no really binding standards as we have in AC. But as you will see, or if you look into the document I referenced, you can translate the AC standards to DC and you will arrive to similar values. So there is something to go by. What is interesting is that it's important to think about the Y capacitors, maybe even more than in AC networks. And when we place the lines next to each other, the differential mode seems to be quite negligible. At least that's what the pilot project suggested. Now, why all this ripple is important and what it should be checked against is the capacitors. In DC system, you have probably a lot of electrolytic capacitors, and one thing that they don't like is oscillations on voltage or current even more. So first thing to check is if the oscillations that we've seen with the transient stability study is within the capacitor limit, and then do the same also for the current, because otherwise the capacitors can age too fast. So this is an important consideration for finalizing the system design. And now, the topic that gets discussed the most, and probably is the most challenging, is how do we protect these systems? Well, the problem with faults in DC is twofold. First of all, your current will start rising extremely fast, reaching very high peaks and releasing a lot of energy relatively fast. But at the same time, the only thing that's holding energy in a DC system is very often the capacitor, unless you have a directly connected battery. If that's the case, your voltage is likely to collapse very fast. So ideally, you want to cut off the short circuit current very fast. And this is where the solid-state circuit breakers come from. Because if we use electric arc to extinguish the short circuit current, we need tens of milliseconds. And that is why in DC systems, especially in the systems that have more installed devices, not just point-to-point connections, we move to using solid-state circuit breakers. Now, I'm not sure if everybody has been acquainted with the solid-state circuit breakers, but here is just a very brief explanation of what is inside of a solid-state circuit breaker. As the name suggests, there is going to be a semiconductor that conducts the current, but also switches it off. The semiconductor needs some sort of energy absorption or voltage clamping. This is quite easy to understand, because if I have a current flowing and I suddenly interrupt it, then that energy is still in the circuit. It needs to go somewhere. This is why we need the voltage clamping. And already it looks like a sort of converter with very weird duty cycle, so you will probably end up with the very same requirements on the control and measurement as you have in any other power electronics converter. What you don't have in converters is the need for electromechanical switch. It is still supposed to be a circuit breaker. A circuit breaker should give you a safe operating. You cannot rely purely on a semiconductor to give you galvanic isolation. You somehow have to add it. And these are the waveform of what I was describing just before. We have a current that starts rising after the fault. We hit some threshold. Then there is a time window when we don't interrupt the current. Why? Because you can have just a load disconnection, something you don't want to act upon. So every manufacturer has some time window. Everybody does it slightly differently, but it is always there. At some point, we finally decide to turn off. The current in the semiconductor goes down to zero. It is transferred to the energy clamping circuit, and that also manifests as the overvoltage. Having the high voltage across the variable resistor, essentially, and the current going to zero dissipates the energy. One thing I think it's important to take away is that unlike electromechanical circuit breakers, in solid-state circuit breakers, you don't have the same limitations, but you do have one particular limitation, and that's the rate of rise of current. As long as the rate of rise of current is lower than some critical value, it's fine, we can interrupt. Why? Because we notice that we have a problem, we have a threshold, but as I said, we have to wait, or there is some delay between the detection and opening. If the DIDT is too fast, the time delay becomes too long, and the current can hit a value where the semiconductor cannot longer interrupt the current in a controlled manner. Inevitably, every semiconductor I know will at some point act as a fuse, but an expensive fuse. So that's not what we want, right? And that's why DIDT is so critical. And this also brings me to my next point. Solid-state circuit breakers are for sure not replacing electromechanical circuit breakers. They enable us to design new systems, but we are not going to design a DC system where everywhere will be a solid-state circuit breaker, or at least not in the next future. So what's the main difference between the two? While at an electromechanical breaker, we have the limitation on the short circuit capacity, we have the amount of short circuit current we can pass, we have the amount of short circuit current that we can open. With solid-state circuit breakers, you pretty much don't have this, because depending on your threshold, your maximum let-through current is defined, given by the DIDT that we discussed, and will be always the same at this critical value. So the main thing to watch out for when using a solid-state circuit breakers, when I simplify, of course, is to check what's the lowest fall inductance that can occur, but also what's the maximum. This is usually not as critical, but it could happen that you have a very large drive or something giving you a lot of inductance. Then the energy stored in the circuit can be a little bit too much for the energy absorbing circuit and can destroy it. ABB has its own first solid-state circuit breaker. as all solid-state circuit breakers, it is very fast. What is a little bit different, it is using an optimized semiconductor that reduces losses significantly compared to other solid-state circuit breakers. Just for giving you a rough idea, this circuit breaker has approximately 1 volt voltage drop at 1000 ampere. If I use 2 IGBTs connected anti-series, then I will probably at the same current have around 4 volts, if not more, depending on the temperature. Maybe 3, depends on the IGBT, but it's quite a big difference. And of course, as solid-state circuit breaker with an integrated mechanical part, it has a very high lifetime. This is because the electrical operations are handled by the semiconductor, not by the electromechanical device, and this increases the endurance. What's nice is the certification. It is, at least as far as I know, the only, well, no, now there are 2, but the other one is very small, like 40 amperes. But in the current category, it was the first and for some time the only certified solid-state circuit breaker. It is still certified by the -2, which is the original standard. But I think end of this year or beginning of the next year, we will have a new standard, -10, and that will be used to certify solid-state circuit breakers. Here is a measurement of the operation. We see in red the current, in gray the voltage. And as I said, the lead-through current is pretty much defined. Of course, what we need to watch out for is the DIDT. One important topic is how do we achieve selectivity, and I touched on this, and I will not go into great detail, but normally we can talk about the selectivity between neighboring sectors or between the big sectors. For example, again, to help myself with the example for marine, here you would have different drives connected to the DC grid via electromechanical switches or fused contactors. And if you have a fault here, there is no selectivity between them. But where you have a selectivity, or you can have selectivity, is of course between the sectors. If there is a fault in this sector, then the solid-state circuit breaker connecting the 2 large sectors will interrupt and will make sure that this part of the system remains operational. And that is why, for the DC protection, the rest of the devices that we have still remains and will remain important. And now, a short design study, because we have 7 minutes. This is about a microgrid that we are currently realizing in one of our locations. I cannot give much more information at this point than that. But how did we start it? I mean, first of all, we checked what loads are we connecting to have an idea on the size. Then we created a concept, and then it got into a more interesting phase where we were selecting the sectors and also what type of protection we will use. The system is quite simple, or this is, let's say, the part of the system that will be realized in DC. It will be connected through an isolated converter to the AC network. It is connected to PV, some passive loads that are unidirectional, and it is connected to EV chargers. One question that is still not clear, as far as I know, is if we will use an isolated converters for the EV chargers or not. There are some advantages to using isolated converters. One of the reasons is that if you have, for example, a battery and an isolated converter, you simply stop switching the converter, and then you don't have the short circuit contribution from the battery. If you have a non-isolated converter here for the battery, for example, a buck boost solution, what's inevitably going to happen, even if you stop switching, there are still the antiparallel diodes that, depending on the topology, can conduct into the short circuit current. So all these things you need to consider. And then in the next phase, also to consider what type of cables do we have and size them appropriately. And this is done together with selecting the droop curves. The droop curves in this example were chosen by colleagues and are not designed by the ODCA rules, but by current OS. But in principle, it's the same. You just achieve slightly different voltages. Then we have used the platform that I mentioned to simulate the currents and the loading and calculate how big the cables need to be. And then we go to the protection phase. What kind of protection devices we need? Because we use the current OS rules, the exact times needed for breaking time in different zones are something that's proprietary knowledge of current OS, and I cannot show that. But it gives you an idea about the time needed, for example, in the main bus, how fast we need to react, and essentially what type of technology we need to use. In the next phase, we looked at the potential faults. Ideally, we simulate all of them and look what's their contribution, or at least the most severe ones. For today, for the simulation, I selected these two, just to give us an idea how the currents will behave in a system like this. I would like to also add, this is a cabled system, so if we have a system connected via bus bars, the DIDTs are even more severe than we will see in the example. So one of the most severe cases, if we have a short circuit fault, pole to pole, on the bus. In that case, all the converters and their capacitors, except for the load, because that has an O-ring diode here, will start contributing to the fault. So the fault current will rise very sharply, and we need to disconnect everything to prevent any damage. Essentially, the conclusion is that all the circuit breakers will trip. This is quite a trivial case. There is no selectivity. What is a little bit more interesting is a case when we have a fault here. I had a very interesting discussion last week with a customer. Do I need a circuit breaker for the in-feed? Just for the record, they have a redundancy in the supplies and an isolated AC to DC conversion. And the argument was, well, you know, I stopped switching, right? So from the AC grid, I have no contribution. The only contribution to the short circuit is going to be the capacitor, and I'm fine with it discharging because the loads, the critical loads, they can ride through the volt zero for several milliseconds and then come back online once we clear the fault and open an electromechanical switch. And at first I was like, okay, that's actually a fair argument. Maybe you don't. But then I was thinking, okay, here's the thing. If I do that, and I have a redundant system here, what's going to happen, everything is going to feed into the fault. And we see it here with the simulation, where the black current is the current flowing into the active front end, and it's essentially a summation of all the currents from the grid. The problem is, I could, in theory, wait out for everything to discharge and reach complete zero, and then start opening my electromechanical device. The problem is the electromechanical device will take 40 milliseconds to open. No load is going to ride through for 40 milliseconds. And if I would design it for such a long ride-through time, I would beat the purpose of having DC because I would need a huge capacitor at that load to supply that kind of energy. Instead, if you use solid-state circuit breaker and, for example, set the threshold here at 500 ampere, the DIDT is not that critical or not super high because we have only 700 volts operation and we have the cables, so this damps a little bit the DIDT. What is important for us is that to look at the grid voltage. We have the fault, the grid's voltage starts to fall, but we interrupt very fast, within microseconds. After detecting the threshold, and then we have some overvoltage because the overvoltage protection is not modeled, but we return back to the operation. Essentially, we were able to protect the system from a shutdown and continue the operation from the batteries. And here we see the simulated operation of the solid-state circuit breaker. This is the overall simulation. Here is the current. You can see the rise. It was tripped at 500 ampere. And then after tripping, there is some overvoltage happening. This is essentially because we still have some energy in the system, and that is going to oscillate. OK, it's exactly 5. So I can end here. Or if you would like to see a short video of a use case from Italy, then I can play that video. OK, so the use case is actually a kind of interesting technology. because it is wireless charging for cars. I remember when I was working at the university here, we also had a wireless power transfer project. As a matter of fact, it was also my master thesis, but then I moved a little bit. And the idea is, okay, if I have an airport, for example, I have a lot of buses. If the buses are standing and charging, the utilization rate goes down. Given a predefined path, I can just have selections where the bus is charging while moving. So dynamic wireless charging can make sense in some applications. And in the use case in Italy, they built indeed 1 kilometer runway with the charging points, and there is an actual bus running. And here is the video explaining the storage. There is also sound. Thank you very much. It was a pleasure to be here.